Good morning. I'm Amy Lensing-Tate, the Executive Director of the University of Wisconsin-Milwaukee Alumni Association. Welcome to our Mobile Master Chat. We're thrilled to have over 100 alumni from across the country with us today to hear from Professor Clark Evans, Associate Professor with our Atmospheric Science Program and affiliate faculty member of the Northwestern Mutual Data Science Institute. He received his bachelor's, master's, and PhD in meteorology from the Florida State University and completed a postdoctoral fellowship at the National Center for Atmospheric Research. He's an expert in the physics, dynamics, and predictability of high-impact weather events, particularly tropical cyclones and squall lines. Clark is an editor for the Monthly Weather Review Journal and chair of the American Meteorological Society's Committee on Weather Analysis and Forecasting. I'll join you again at the end of the chat, but now it's my pleasure to turn things over to Professor Evans.
Great. Thank you very much, Amy, and welcome everybody. I hope you all are staying warm in these cold and snowy times. Today we'll think a little bit of warm thoughts as we turn our focus to the hurricane season and in particular the Atlantic hurricane season of 2020. So in the next 30-35 minutes or so, it's my hope to step through the basics of hurricane science as well as present that through a bit of a lens from the last year with the record-breaking Atlantic hurricane season of 2020. So if we could go ahead and move on to the next slide. So first, a brief outline of where we are and where we're going. So we'll start off with a bit of a climatology. And by climatology, you can think of that sort of like a genealogy. Where do they occur? When do they occur during the year? Sort of the basic vital statistics. And then we'll sort of step through the life cycle of tropical storms and hurricanes. We'll start by describing how they form. Then we'll move on from there and describe a little bit about how they gain intensity. From there, we'll move on to describe a little bit about how they move, as well as describe the end stage of their life cycle, what leads to their decay or to their dissipation. We'll wrap everything up with a discussion about how do we actually predict these storms, both their track as well as their intensity, where they are and how strong they will be when they get there. So if we move to the next slide. So first, let's describe a little bit about what is a tropical cyclone. And I'll use that generic term tropical cyclone throughout much of the talk here rather than tropical storm or hurricane. A tropical cyclone refers to either one of those. It's independent of the wind speed. And we'll talk a little bit about what distinguishes a tropical storm from a hurricane in just a couple of slides here. But whether we're talking about a tropical storm, hurricane, or just that more generic tropical cyclone, there's a few key characteristics that distinguish them from other types of cyclones, like those that we see here in Wisconsin. In particular, they are what we call non-frontal. So in the image there at left, there's a depiction of what we would call a mid-latitude cyclone, like what we see in Wisconsin, with a cold front extending to the south, as well as a warm front extending to the east in blue and red, respectively. Tropical storms and hurricanes don't have fronts associated with them, which means that they don't have large temperature changes from warm out ahead of it to cold back behind it in association with them. So if we go to the next point. Little bit of a Family Feud connection for those of you who might be familiar with the game show. But in addition to them being non-frontal, if we click to the next point here, they're also what we call synoptic scale. And this refers to both a distance scale. In this picture here, we have Hurricane Michael from 2018 that hit the Florida Panhandle during the month of October. And the spatial dimension on this figure is over 700 miles from west to east and over 700 miles from north to south. So that defines sort of the spatial extent that we see hurricanes, but we also have a time extent associated with them as well, typically on the order of 5, 7, 10 days, depending on this individual cyclone. But in addition to them being synoptic scale features, we typically find them only over tropical or subtropical waters, where tropical refers to locations closer to the equator, subtropical regions are places closer to, say, Bermuda and Florida, so still to the south of where we see Wisconsin. What I have depicted here at left is the average sea surface temperature over the North Atlantic basin during the month of August. This is depicted in degrees Celsius. The black line that I have added in there is the 27 degrees Celsius isotherm, or line of constant temperature. That's around 80 degrees Fahrenheit. So everywhere to the south and west of that black line has average water temperatures of 80 degrees or warmer during the month of August. And anywhere to the north and to the east of there has average water temperatures that are colder than that. Our tropical storms and hurricanes primarily form and exist in the regions that are warmer than that 80-degree threshold. We'll talk a little bit about why as we move forward. In addition, tropical cyclones have persistent organized thunderstorms. Here I have a cross-section view. If you take a slice straight across a hurricane, you would find the thunderstorms concentrated very near to the center of the storm, sort of this area that's depicted with a B near to the ocean surface in the diagram. These thunderstorms play an important role in taking the heat that's gained from the underlying ocean surface and spreading that upward throughout the lower portion of the atmosphere. And it's that heat that helps to fuel the tropical cyclone's winds. And we'll talk a little bit about that too as we go forward. In addition, tropical storms and hurricanes have what we call a closed cyclonic circulation. So cyclonic refers to the direction in which the winds turn. In the northern hemisphere for a tropical storm or hurricane, that's counterclockwise, whereas in the southern hemisphere, that would be clockwise. Before a tropical storm or hurricane forms, the wind field might look like what we see in the upper left picture labeled pre-formation, where those wind barbs, the lines depicting the wind field, kind of turn in a counterclockwise fashion, but they don't necessarily form a completely closed circle in that counterclockwise fashion. Whereas once the tropical storm or hurricane has formed, they look more like what you see in the bottom picture labeled post-formation, where you can see a clear counterclockwise turning to the wind barbs, depicting a closed cyclonic rotation. Then finally, tropical cyclones have what we call a warm core structure, and that has two elements associated with it. Given that they are driven by heating from the underlying ocean, they tend to be warmer near to their center as compared to areas further away. The temperature difference is not that large. Recall that we said that they're non-frontal, so we don't have these large contrasts between warm and cold air clashing on either side of the storm, but rather a modest warm anomaly near to the center of the hurricane or tropical storm, and somewhat less warm as you move further away from that. But in addition to that warm anomaly, we also have the change in intensity of tropical storms and hurricanes with increasing height. Unlike mid-latitude systems where the strongest winds are found up at jet stream level, for tropical storms and hurricanes, they're found very near to the surface, and they get smaller as you go upward from there. So keeping all of those elements in mind, we want to talk a little bit about the climatology or the genealogy of tropical storms and hurricanes. So first we'll ask and answer the question, how many do we typically see in the Atlantic Basin in any given year? And this depiction here shows the evolution from January 1st through to the end of the year. And at any given point along that time period, how many storms in the yellow, hurricanes in red, and what we call major hurricanes in the purple we would have expected to see. By the end of the year, by the end of the season, on average, we see just over 11 tropical storms in the Atlantic Basin. Just over 6 of those become hurricanes with winds of 74 miles per hour or greater. And just over 2 of those become major hurricanes with winds of 111 miles per hour or greater. We refer to hurricanes by their wind speed in terms of category 1, 2, 3, 4, 5. And those are all dependent upon their wind speed from 74 miles per hour well up over 160, 170 miles per hour. I've added in annotations here with the stars for just what we saw during the record-breaking 2020 hurricane season. The number of named storms was 30, well off the top of the chart. If I wanted to be able to depict this, I would have had to make the chart really, really small just to be able to fit the 30 where it should be. We had 13 hurricanes, so we had more hurricanes last year than we see even in the total number of tropical storms during an average season. And we had 6 of those major hurricanes, the most damaging of hurricanes last year, including hurricanes Laura that hit Louisiana, as well as Eta and Iota that hit Central America very late in the season, causing catastrophic damage down there. So in all, 2020 was very, very atypical relative to this normal climatology of how many storms we would expect to see. So if we go forward to the next slide. So a little bit more about when during the year do they occur. Instead of those cumulative plots that we saw on the previous slide, here we're looking at instantaneous numbers of how many tropical storms in the red and how many hurricanes in the yellow you would expect to see per 100 years on any given day during the Atlantic hurricane season. So this 100 here, since it's 100 per 100 years, means that on average on that day, you would expect to see one storm somewhere across the Atlantic basin. So the largest number of storms occur roughly between the start of August and about the middle point of November, with the peak occurring on September 10th in terms of both the number of tropical storms and the number of hurricanes. Hurricane season officially begins in the Atlantic basin on June 1st with a slow buildup through June and July, and it officially ends on November 30th with a pretty rapid decrease as you go from the middle point of October through to the start of December. But down here at bottom, we have depicted what happened during 2020. I lined up the time axis here so that you're going from May on the left through to December on the right. And we find that we saw storms forming even before the official start of hurricane season, with Arthur and Bertha here into the month of May. We had our third storm, Cristobal, which came within 1.5 miles of actually reaching Wisconsin as a tropical depression here at the very early part of June. And then this buildup all through June and July, such that by the time we reached the start of August, we had already had 9 storms, almost a full season's worth of activity on average within the first 2 months. Then we hit the actual peak of the season and saw many, many storms from Tropical Depression 10 and Tropical Storm Josephine in early to mid-August, through Kyle, Laura, Marco, Omar, Nana, all the way down through Beta, Wilfred, Alpha. We got into the Greek alphabet in the month of September, and then continued through 8 letters of the Greek alphabet for naming our storms over the course of the remainder of the hurricane season. So the way the storms were distributed last year was very similar to what we expect to see during a regular season, but there were many more at any given point of the season than we would expect to see. So having briefly discussed a little bit about when and how many, we can discuss a little bit about where. And we kind of hinted at this early on in the overview of tropical storms and hurricanes. They form in the tropical North Atlantic, which is what we would call the main development region. That's sort of this area between the South American coast and the African coast, well away from North America. But we also see a number of them form in the Bermuda Triangle region, sort of to the east of the southeast United States, out toward Bermuda, and to the north of Cuba, Hispaniola, and Puerto Rico, as well as within the Gulf of Mexico and the far western portions of the Caribbean Sea. That red line here is the same as that black line on the sea surface temperature diagram a few slides back. That delineates where, during the peak of the hurricane season, the waters are typically warm enough to support tropical storm formation versus cold enough to inhibit it. And most of these blue dots, which are individual formation locations for tropical storms and hurricanes, are found in the warmer region relative to that red line, with just a few exceptions across primarily the far northern reaches of the Atlantic basin. Now, if we click forward one slide or one annotation from here, I added in all of the locations where 2020's tropical storms and hurricanes formed with the silver stars. And by and large, they formed within these regions where the water temperatures are typically above 80 degrees Fahrenheit. The one notable exception here was one of the Greek-lettered storms near to the Iberian Peninsula. That was the first storm to make landfall as a tropical or subtropical storm on the Iberian Peninsula in recorded record. We had clusterings of tropical storm and hurricane formations here just off of the coast of the southeast United States, a few within the Gulf of Mexico, multiple storms within the Caribbean Sea, and then several out here in the main development region between South America and Africa. So if we go forward to the next slide. So I want to take a step through a representative tropical storm. Here in this case, tropical storm, later Hurricane Dorian from 2019. Those of you who are well versed with hurricane history may recall Dorian as the storm that devastated the Bahamas during the middle of the 2019 hurricane season. But in this video, we're primarily looking well before that time period when Dorian just was first organizing from a tropical disturbance, no name, no classification, into a tropical storm when it reached strong enough winds to acquire the name Dorian. And as we go through this video, we'll step through it a few times here. We see that the clouds, in particular the colored clouds, which denote thunderstorm regions, the darker the colors, the deeper and stronger the thunderstorms, they pulse over this 2-day period here. There are periods of time where there are very few of those thunderstorms, primarily the lower white milky clouds closer to the surface of the ocean. And then there are times where there are deeper thunderstorms concentrated near to the center of that rotating mass. These thunderstorms play two vital roles. One, they're serving to gradually moisten the atmosphere surrounding that disturbance. Tropical storms and hurricanes are very moisture-laden disturbances, but they're not invincible to infiltrations of air from the surroundings, which are not as moist. We'll talk a little bit about that as we step forward into some of the necessary conditions for tropical storm formation. But these thunderstorms that form near to the center initially help to play that vital role in terms of moistening the atmosphere. And they also play a vital role in distributing the heat that comes from the underlying ocean surface upward to build that warm anomaly. So we'll talk a little bit about the necessary conditions here and start with that warm ocean surface. So as noted a couple of times before, tropical storms and hurricanes are warmer than their surroundings, especially not just right at the ocean surface, but as you get up higher within the atmosphere. There is heat that is gained from the underlying warm oceans that the thunderstorms help to loft upward within the tropical storm and hurricane center core. That warmth is important because it reduces the sea level pressure that whenever you see a high or a low on a map, they're referring to sea level pressure. This warmth within that column for the hurricanes or tropical storms helps to, my apologies, my computer was giving me a little bit of an error message there. So this warmth within the column helps to reduce the sea level pressure, creating that low pressure near to the surface. And the change in pressure from that low pressure outward away from there is what drives the storm's winds. So that warmth not only reduces the sea level pressure, but also increases that cyclonic rotating motion around the storm. Just how strong that pressure decrease is, how much that warmth is, governs how strong those winds can actually become. So if we step to the next bullet point here, this warmth that the storms gain from the underlying ocean comes in what we call sensible and latent heating. We have two little bullets here that we can go ahead and put up on the screen to describe what each of those are. But in general, sensible heating is related to the temperature difference between the ocean, which is relatively warm, 80, 82, 84 degrees Fahrenheit, and the air that resides just above it, which is usually about 1 to 2 degrees Fahrenheit cooler. So that warmth is directed upward, and that provides some of the warmth that the storm can use to fuel its winds. Latent heating, however, is the primary energy source for tropical storms and hurricanes. And this is associated with the evaporation of water from that underlying surface to moisten the atmosphere. There is an amount of heating associated with that once that water vapor from the underlying ocean is lifted upward, it condenses once again into liquid precipitation and then eventually freezes as you get further above the ocean surface. And there's heat that is released due to those phase changes of water, and it's that heat that provides the primary fuel for tropical storms and hurricanes. You can think of these water temperatures like octane when you're filling up your car at the gas station. Cooler water temperatures can be viewed sort of as lower octane fuel, whereas higher water temperatures can be viewed as higher octane fuel. The warmer the water temperatures, the more heating that is possible to be realized, and the greater the potential intensity for the storm can achieve. So if we go to the next slide. In addition to these waters, we need some sort of precursor cyclonic or counterclockwise rotation. And this is necessary so that we can organize that heating and organize the thunderstorms around a central location to be able to take that heating and spread it upward within the vertical. So if we add in the next bullet here, Most common features that lead to tropical storms and hurricanes are features such as African easterly waves, and the diagram here at left is an example of an African easterly wave having progressed from east to west in the tropics, in this case located near to Hispaniola and Puerto Rico, with this broad but weak cyclonic curvature given by the red lines with the arrows here, prior to a tropical storm or hurricane forming. We can also see features such as mid-latitude fronts. If they reach out over to the warm ocean waters of the Atlantic Basin and sit there for a prolonged period of time, they can undergo a dramatic transformation into a tropical storm or hurricane. Usually, mid-latitude fronts are a common precursor during the very early and very late parts of the season. African easterly waves and similar phenomena are those that are responsible for the vast majority of our most intense storms, as well as the majority of those during the middle of the season. So if we go to the next slide. We also need moisture and ascent. And this, combined with what we'll talk about on the next slide, are sort of the anti-fuel for tropical storms and hurricanes. Again, tropical storms and hurricanes are areas that are moister than their surroundings. The thunderstorms help to moisten that, and once they have become sufficiently moist, the thunderstorms can persist. And we'll see that in another satellite loop from Hurricane Dorian in just a few moments. So we need it to be moist, and we need there to be that cyclonic rotation. That friction leads to air converging near to the center, and that forces air upward, which allows for thunderstorms to form. If you have dry air, like what we see in the depiction here at left, the yellows and the oranges depict dry air from the Saharan desert of Africa infiltrating the northern half of a disturbance here in the main development region of the tropical North Atlantic. This drier air, when it comes in, helps to squelch thunderstorm activity. You can think of this sort of like ventilating your home, that if you open up a window on one of the cold nights or cold days even that we've had in Wisconsin lately, you're going to lose the heating that your furnace has worked so hard at developing inside of your house, and you're going to be bringing in that colder outdoor air in there. Just as that's not very good for your well-being and comfort, or for your pipes for that matter, bringing in dry air from the outside is not very good for tropical storms and hurricanes as thunderstorms. It leads to the dissipation of the thunderstorms. It cools the environment as you go from liquid and frozen water back to a vapor. And so the fuel that it could gain from the underlying water has to go into rewarming the air rather than going into fueling the tropical storms and hurricanes themselves. So if we'll go to the next slide. The way that this dry air from the environment often gets into a tropical storm or hurricane is through what we call vertical wind shear. And this is a change in the wind speed and/or direction with increasing height. And so the cartoon that we have depicted here at left depicts a case where there is very little change in wind speed or direction with height at left, called low wind shear. So that gray cloud mass can be viewed as the thunderstorms near to the center of the storm. The heating that the storm has gained from the underlying ocean is concentrated within that column of thunderstorms. It's upright. The vertical wind shear is not able to tilt that over. Whereas in the depiction at right, the case where you have a strong change in wind speed as depicted here, but also possibly direction, causes those thunderstorms to become lopsided or concentrated primarily on one side of the storm as opposed to all around the storm. So you're taking that heating from the underlying ocean and spreading it out over a larger horizontal area. When you do that, the pressure decrease at the sea level that you see beneath that becomes smaller. And so the change from the storm to its surroundings becomes smaller. And so the wind speed associated with the storm also becomes smaller. But as mentioned on the previous slide with the dry air, this vertical wind shear, when it is large, also serves as sort of the window opener, to use our previous analogy. It's what actually helps to push the dry air from the environment into the tropical storm near to its center. So the combination of large vertical wind shear and drier air in the environment can be viewed as that anti-fuel against the high octane fuel from the warm underlying ocean. So tropical storm and hurricane formation, as well as intensification or intensity change more broadly, are sort of a battle between fuel and anti-fuel over much of their lifespan. So if we go to the next slide. So with all of that in mind, we can ask the question, what about 2020? We saw 30 storms, many of which became hurricanes and many of which became intense hurricanes. And so we could put the hypothesis forward that everything must have been more favorable, that you had abundant warm water, that you had low vertical wind shear, and a very moist environment with many precursor disturbances present within the Atlantic Basin during 2020. And by and large, that holds true. In particular, the regions where we saw most of our storms form, recalling back to our depiction with the silver stars, the Western Caribbean Sea, the Gulf of Mexico, and the Gulf Stream off of the Southeast United States coastline, each had better than normal, more favorable than normal conditions for tropical storms and hurricanes to form. Above normal water temperatures, around 85 degrees Fahrenheit in each of these locations. Above normal moisture, so the atmosphere was pretty moist, not a lot of dry air could be brought in. And there was below normal vertical wind shear. So even if there was drier air, it would be more difficult to bring that into the storm. In addition, the western North Atlantic, that area just off of the coast of the United States, stretching out toward Bermuda, also featured a pattern that readily allowed for mid-latitude fronts, especially early in the season during the months of June and July, to stall out over the warm Gulf Stream or warm North Atlantic waters in what we call a modestly favorable, so low wind shear, high moisture type of environment. And over the period of several days, those disturbances would spawn up tropical storms of their own as well. In the tropical Atlantic, further out between the coast of South America and Africa, we had fewer than normal Saharan air outbreaks, where the desert air from the Sahara is kind of kicked up by the strong easterly tropical winds and carried outward over to the Atlantic Ocean. A lot of times in the summer, you'll see in the Caribbean islands, Florida, and the Gulf Coast, hazy periods where you get some of that Saharan air kicked up and transported across the entire basin. But we really didn't see that during the year 2020. And that's in large part because rainfall on the southern edge of the Sahara, where the African easterly waves preferentially form and track, was quite a bit above normal. So the air was moister and the ground was moister. So you couldn't as readily kick up dry air and spread that out into the Atlantic to inhibit storm formation throughout much of the season. So 2020 was kind of like a perfect storm in many ways, as we saw not just in weather, but beyond last year. There's really a perfect storm of positive ingredients for tropical storm formation across much of the Atlantic Basin. So here we revisit our video loop of Tropical Storm Dorian, and we pick up with where the previous video left off when it was a weak tropical storm. And this one will go through quite a long period of time as the storm approaches the Caribbean islands and then progresses northwestward past Puerto Rico and toward the Bahamas, where it ultimately stalls out. In this video, note how the yellows and the oranges and the reds are very persistent near to the center of the storm. Unlike in the initial development stage, thunderstorms are more or less quasi-persistent. They maintain over periods of days as the storm continues to progress to the west and to the northwest. When the storm reaches a sufficient intensity, usually when it becomes a weak hurricane with winds of 75 to 90 miles per hour, we get the development of that characteristic eye, that area without thunderstorms near to the center of the storm. And here Dorian stalls out near the northern Bahamas for several days, and we see that eye dissipate and become replaced by a much more ragged, much larger eye-like feature before the storm approaches the Carolina coastline and then progresses onward to the north and to the east. We'll revisit this portion of the video a little bit later on when we talk about the decay stage of a tropical storm or hurricane. But the part that I really want us to focus upon with that video was that first half there. With persistent thunderstorms that become even more persistent, the colors associated with them become more consistently red and orange, and you get that initial development of the eye. What is happening during that time period to lead to the increase in wind from 35 knots or 40 miles per hour at the start of the video? And we see that number in the upper left of the video keeps going up as the storm becomes stronger and stronger. 75 knots or 85 miles per hour, a Category 1 hurricane. And now we're going to reach the period where it rapidly increases. 100 knots, 115 miles per hour, 115, 120, 125 knots, 130. We're up around 155 miles per hour at this point. 160, 175, 180 miles per hour as it approaches the northern Bahamas. What is happening during that time period? So if we go ahead and click to the next slide. So how does that fuel that we get from the underlying ocean go into actually leading to that increase in wind speed? This is what we call the process of wind-induced surface heat exchange. So breaking that down, wind-induced implies that the wind, that cyclonic rotation around the storm, has something to do with it. And that's the mechanism that helps to facilitate the extraction of that energy from the underlying ocean. And surface heat exchange is just that exchange or extraction of the heat, both sensible and latent heating from the underlying warm ocean. This is all wind speed dependent. When you have a weak wind speed, that energy exchange is relatively weak. And so we start off with that weak surface heat exchange, and those initial thunderstorms that we saw develop near to the beginning of the tropical storm's life cycle help to spread that heating upward throughout the lower portion of the atmosphere. So if we click to the next box, once that's occurred, spreading that heating upward through the lower portion of the atmosphere leads to that warm anomaly. It's warmer near to the center of the storm, especially 3, 6, 9 miles above the surface, as compared to areas that are not within the storm. And so that warm anomaly helps to reduce the sea level pressure beneath the storm. So if we click to the next box, and then that in turn leads to low pressure near to the center, compared to higher pressure away from the center. And that change in pressure from low to high creates the winds associated with the storm. So that's sort of the horizontal pressure difference part of this. The reduction in sea level pressure also increases what we call the air-sea disequilibrium. And that's really a fancy term for that change in temperature and change in moisture content between the ocean and the air that resides just above it. Reducing the pressure actually, while keeping the temperature constant or even increasing the temperature, actually increases the amount of moisture that the air can hold. So it goes from the ocean, which is completely moisture laden, to an atmosphere above that can hold even more than it could before. So it makes it more efficient at being able to grab moisture, latent heating from the underlying ocean. The increase in that horizontal pressure difference increases the wind speed, and the increase in the wind speed, as well as the air-sea disequilibrium, that change in temperature and moisture in particular between the ocean and the air, both of them go into increasing this rate at which you can gain energy from the underlying ocean. And that then feeds back upward through the thunderstorm. So we kind of get this feedback loop that you get an initial amount of heat, spread it upward, and modestly intensify the storm. And then you can get more heat and spread that upward and intensify the storm to allow you to get more heat, and so on and so forth. So that area that's depicted here in the gray is that which is associated with the tropical storm intensification. We already assume that we have something that has gotten us to tropical storm status. Now that we are there, going up from tropical storm status through hurricane status is associated with this feedback loop depicted in gray here. The warmer the underlying ocean, the greater the potential intensity, all the way up to what we call the maximum potential intensity, which is where friction over the overlying ocean becomes so large that that fuel from the underlying ocean can't overcome it any longer. And usually that maximum potential intensity is way up in the order of 150 to 200 miles per hour. Most storms, fortunately, come nowhere near reaching to that maximum potential intensity. But there is a break on this. We do not see a physical scenario where a storm could reach 300, 400 mile per hour winds. Fortunately, friction near to the ground helps to provide a break on that. So if we click ahead to the next slide. So having described a little bit about the energy source, we can talk a little bit about where they go once they have actually formed. What I have depicted here at the upper left are climatological or historical tropical cyclone tracks over many, many hurricane seasons. These individual lines, like pieces of spaghetti, depict where a storm originated, usually on the south and east portions of the diagram, and then tracked, going in a clockwise fashion to the north and then eventually toward the east as they reach to higher latitudes. Tropical storms and hurricanes typically track around areas of high pressure, like the Bermuda High, that are located in the lower to middle atmosphere. And that gives rise to that clockwise turning to the pieces of spaghetti. And we see the summertime average lower atmosphere winds. We see the Bermuda High, so named because the center of it is located near or sometimes just east of Bermuda here in the bottom diagram. So you can kind of think of tropical storms and hurricanes, their movement like sticks in a river. When I'm teaching a tropical meteorology class, I like to go to the Milwaukee River outside of Grafton, where I live, and just throw a stick into the river and watch it track along with the overall current. Yeah, there are bumps and obstacles within the flow, but by and large, a stick that I throw out in the river upstream is going to be carried downstream by the river's current. Likewise, a tropical storm and a hurricane, though there are bumps and ebbs in the flow, is largely going to be steered around the subtropical high, the Bermuda High or similar features within the lower portion of the atmosphere. So in general, this is what leads to tropical cyclones moving from east to west when they are further to the south, before eventually turning north and then eventually northeastward as they reach to higher latitudes. So if we go to the next slide, we can naturally ask the question, what about 2020? And 2020 adds a lot of lines of spaghetti to the historical track plot. Each one of these lines colored based upon the intensity of the storm, with tropical depressions, winds less than 39 miles per hour in green, tropical storms, winds 39 to 73 miles per hour in yellow, and hurricanes in red and pink with winds of 74 miles per hour or greater. This is the set of tracks for all 30 tropical storms and hurricanes that formed during the 2020 Atlantic hurricane season. By and large, most of them started out here in the main development region between South America and Africa, here in the Western Caribbean, or here in the Gulf of Mexico or off of the southeast coast of the United States, and tracked from east to west before turning north, roughly between about 20 and 30 degrees north latitude, as you get to around the latitudes of Cuba and Florida, before turning more toward the northeast as you get above the latitude of Florida, so sort of the southeast United States. And if we click forward, I've annotated in the predominant tracks of where these storms formed. And you can see that they all have this sort of clockwise turning from east to west before turning northward and then northeastward as they complete their life cycle here. With the preferred regions, again, near to the United States and North America more generally, a couple out here into the main development region, typically recurving nearer to the east of Bermuda, before moving harmlessly out into the North Atlantic, and a couple here at very high latitudes into the far northeastern Atlantic basin last year. So moving forward to the next slide. So we come back to our video of Tropical Storm and Hurricane Dorian, and we'll let this go through to the point of reaching to the Bahamas, and it'll be that time period after the Bahamas through to the end of the video that we're most interested in here. So in this case, what happens when a tropical storm is nearing the end of its life cycle, or more generally is beginning to decay? There are four primary causes of tropical storms decaying or weakening, or ultimately completely dissipating. The first one that we'll see as Dorian reaches near to the Bahamas and ultimately stalls out is cold water. Usually, tropical storms and hurricanes experience cold water when they get to very high latitudes, say 35 degrees, 40 degrees north latitude, getting to about as far north as Illinois and Wisconsin are located. In Dorian's case, it just set over the same water for such a long period of time that it sucked up all of the energy from beneath it and actually led to it cooling down to the point that that water could no longer sustain an intense storm. So it helped to suck in cooler water, lower octane fuel that led to the storm ultimately weakening. The second one that we see here as Dorian is moving away from the Carolinas is associated with landfall. When a storm moves over land and encounters or loses the warm oceans from which it originated, two important changes take place. One, the friction over land is much, much higher than it is over water. Anybody who's been out on Lake Michigan or even some of the smaller interior lakes of the Midwest knows intuitively that the wind is typically stronger out over the ocean, out over the water, than it is over land. And that's because of the rough effects of land, buildings, trees, other obstructions that help to slow that wind down. But also over land, there's not as much water in the ground. I mean, by definition, it's not a water-laden surface. And the ability to extract out heat in the form of sensible or latent heat is much, much lower over land than it is over the ocean. So even if there was a lot of water and a lot of heat in the ground, we wouldn't be able to get that out to fuel the storm as readily, and we would have a lot more friction to try to lower the wind speed, counteracting that fuel. As Dorian moves further to the northeast from the Carolinas, we see two other effects take place. The first one is the anti-fuel. You see thunderstorms in the yellows, oranges, and reds on this satellite become confined primarily to the north and northeast of the storm. That says you get that strong vertical wind shear, fast winds at higher altitudes out of the southwest in this case, causing drier air to infiltrate the storm that leads to thunderstorms being favored only on the side away from that. It's like opening up a window to your house on a cold night. The area, your whole house gets cooled down, but the areas closer to the window cool down the most. They see the greater negative effects relative to the areas on the other side of the house. So Dorian experiences that as it nears the end of its life cycle. But then at the very, very end of the loop, and we'll let this come through to that point one last time, Dorian undergoes what we call an extratropical transformation. It starts out as a tropical storm and hurricane, but then ultimately becomes like a mid-latitude cyclone that we see here in Wisconsin by the acquisition of fronts as it interacts with the temperature difference that we see between the higher latitudes and the tropics during any given point of the year. So we'll let that loop through. Looks like the loop's kind of struggling a little bit here, but at the end, note how Dorian changes from this sort of more cyclonic area of thunderstorms with a eye near to the center, and it gradually acquires more of that comma shape, like you see with cold fronts and warm fronts here in the Midwest. So if we go ahead to the next slide. All right, so with all of that in mind, we've talked a little bit about where storms form and when they form, how they actually form and gain intensity, and the processes by which they ultimately dissipate or decay. How can we forecast all of that? So I wanted to close this presentation with a brief discussion about how we can forecast tropical storms and hurricanes. We have two primary things that we're interested in. Where are they going and how strong are they going to be? And three types of models. Ones that use statistical relationships with atmospheric parameters, what we call dynamical parameters. Dynamical models, which are things that you'd see TV meteorologists when they show future projections of the weather, that's what they're showing you output from, a dynamical model. And then consensus models, which are averages of different models, multiple different models in creating a forecast. So if we go to the next slide. The output from these models, and this is an example from Tropical Storm, later Hurricane Laura from the 2020 hurricane season, look like lines of spaghetti on either maps, like we see here at left, or charts of intensity, where you have intensity on the vertical or y-axis and time here on the horizontal or x-axis. Each different line is the output from a different model, and forecasters are using this information, plus their intuition, as well as other pieces of information like observations, to come up with their forecasts. So if we go to the next slide. We have an example on the left here of a number of different National Hurricane Center forecasts from LoRa with the different colors, from the blues and greens depicting earlier in LoRa's life cycle to the reds, oranges, and pinks depicting later on in LoRa's life cycle. You can see that all of the lines are generally oriented in the same direction through to Louisiana, where LoRa ultimately made landfall, before turning to the north and to the east at the end of LoRa's life cycle. The depictions here at right provide measures of how good this forecast is. How far away was the forecast position from the actually observed position from a day out to 5 days in advance? And then on the right side is comparing that to what we call a no-skill model, basically based off of historical storms or persistence for LoRa. Where would we have expected it to go, and how much better are the forecasts, like you see in the lines here at left, than that no-skill model? In general, errors are small at 1 to 2 day lead times and get larger as you go further out. But the improvement relative to those no-skill models depicted by the bars, and the long-term average of that is in the black line here, actually gets better as you go out further in time. So if we go to the next slide. I guess there we go. So we have a little bit of a history of how well we have been able to forecast. And each of these different colored lines, red is 1 day, green is 2, yellow is 3, brown is 4, and blue is 5-day forecasts from 1990 through 2019 here for track errors, how far away, and intensity errors, how different in the strength of the storm. The lines are all directed downward and to the right, which means that the errors are getting smaller with time. They're getting smaller with time faster for track and less so for intensity, which is a lot harder to predict because it's reliant on small-scale thunderstorm details that are very hard to observe and very hard to reliably predict in the chaotic atmosphere. So if we go forward, we sort of reached the end, and I just wanted to very quickly summarize that tropical storms, or tropical cyclones more generally, are most common in the summer and fall when the oceans are relatively warm. They gain their heat from those warm oceans, they track clockwise around areas of high pressure, and decay whether they make landfall, cold water, or encounter large vertical wind shear. 2020 was particularly noteworthy for having a lot of storms in a persistently favorable environment. And in addition, what we didn't cover is just how many of them gained intensity rapidly right before landfall. Laura near Lake Charles, Louisiana is a good example. Iota down in Central America is another good example of this, owing to anomalously favorable conditions, especially warm waters and low vertical wind shear across the ocean. So with that, if we move forward to the last slide here. So that's all that I have for you all today. I hope you all have enjoyed sort of this 45-minute primer on hurricane science with an eye to the 2020 Atlantic hurricane season. Thank you all for joining. Thank you to the UWM Alumni Association for having me, and to Amy and Abby for helping to host this event. You can reach me via email, Twitter, or through my website, and I'm happy to take whatever questions may be here. Thank you.
Great. Okay, we have our first question, Clark. Is the transatlantic transit of Saharan sands a modern phenomenon due to climate change, perhaps, or something that has occurred throughout recorded meteorological history?
That's a really great question, Richard, and thank you for asking that. Uh, it's not specifically a modern phenomenon. It's been present for as long as the Sahara has been present. Of course, if you go way back in geological eras, certainly it would be different as you get back hundreds of thousands of years. But the prevailing winds at the latitudes of Africa are primarily out of the east and have been for quite some time. And the Sahara has been desert-like for quite some time. So I think what's more unique about it now is just our understanding of it. Only within the past 60 or so years have we had satellites to be able to track and identify features like the Saharan air layer from their origination over Africa, across the Atlantic basin toward North America. So our understanding and ability to track it has certainly improved over the last 60 years, but we have reason to believe, especially through paleoclimatology, soil records, that the Saharan air layer has been present for quite some time.
And then there's a question that came in before the chat, before we get to Katie's question. How often is Wisconsin adversely affected by hurricanes?
Incredibly rarely, which was an interesting question that I had myself when UWM was looking to hire somebody 10 years ago with expertise in tropical storms and hurricanes. Like, why Milwaukee? There's not really hurricanes or tropical storms impacting there. Cristobal was so rare in the 2020 hurricane season because it came so close to Wisconsin as a very weak tropical depression. We're too far away from the warm waters of the Gulf of Mexico or the Atlantic. And by the time that a storm reaches to our latitude, it's almost always transformed into a non-tropical area of low pressure. So it's incredibly rare, fortunately, to see something like that. Wisconsin's really fortunate more generally to not have more natural disasters than it does, cold and snow of the last couple of weeks notwithstanding.
And a question from Katie, are there hurricanes on other planets?
Great question, Katie. So there are hurricane-like disturbances. I wouldn't necessarily call them hurricanes per se, but we do see intensely cyclonic rotating features on other planets. Looking at Jupiter, the gas giant, for instance, you'll see cyclonically rotating features there. There's been some theoretical work that shows that you can get hurricane-like disturbances even without underlying warm oceans, but rather just a very large change in temperature between the surface and the lower portion of the atmosphere. The dynamics of these features are not very well understood, but it does appear that we can see hurricane-like features on other planets.
That's fascinating. All right, let's see if we have any other questions. You mentioned a tropical depression, almost making it to, oh, we had that already. You just covered that one. So it was a burning question for a few people on the chat.
I was really hoping that Cristobal, just for the sake of sheer curiosity, would have actually crossed the state line. But the point that the National Hurricane Center in their final analysis was literally just across the Mississippi River in far northeastern Iowa. It would have been the first one, I think, still as a tropical storm or tropical depression to have made it into Wisconsin as such. Just didn't quite get there.
2020 would have been the year it should happen too, right?
Absolutely.
Okay, another question from Richard. If a storm crosses the equator, will it reverse rotation? If not, what happens? To clarify, if an already formed storm crosses the equator, will it reverse rotation?
Yeah, that's a really good question as well, Richard. And when we have an already formed storm, it's really hard for them to be very close to, especially within shouting distance of crossing the equator. The rotation of the Earth creates a Coriolis effect, and in particular, the variation in that as you go away from the equator, where that effect is near zero, toward the poles, where it is maximized. That effect creates a drift for tropical storms and hurricanes that tries to take them away from the equator, whether it be to the north in the northern hemisphere or to the south in the southern hemisphere. So as they're tracking to the east within either hemisphere, that force associated with the Coriolis effect is trying to keep them away from there. But you can see very weak disturbances when they're just forming near to the equator, and sometimes they will cross from one side to the other. We saw one just in the past week or so out into the Western Pacific. But when they do so, they're so weak that they haven't really organized sufficiently for the differences in the rotation of the Earth's effects, that Coriolis effect, to have much of an impact on them one way or the other. And so there's not much of a change that you see for those weak disturbances, and the stronger ones tend not to approach there at all.
Good question. Excellent question, Richard. Now, what caused Dorian to stall? Do most cyclones have a period where they do stall?
That's a great question as well, Renee. Thank you for asking that. So a lot of times when a storm stalls, it's usually located between, I guess to use an analogy, a rock and a hard place. It kind of gets stuck, that you have the area of high pressure, usually off to its north and to its east, and you have another area of low pressure off further to its north and to its west. And consequently, the storm is stuck in the area between the two where neither really have an influence on its motion. So it just kind of stalls out there until either the high pressure builds further to the west and kicks it to the north and west, or the area of low pressure builds in from the west and kicks it further to the north and to the east. Most cyclones don't necessarily have a period of time where they stall, but there's some evidence to suggest that slowing of storms is becoming somewhat more frequent. And when they do so, it tends to be when they're starting that turn from moving east to west to moving more northward and then ultimately toward the east, which unfortunately happens to be in the subtropics, closer to a lot of the populated land masses of the Atlantic basin. So it appears that we are seeing an increasing trend in the number that stall near to populated areas.
Last year, Puerto Rico and the Virgin Islands had minimal activity, even though it was such a big year overall. Does it depend on where the storms originated? More in Western Caribbean?
Yeah, that's a great question, Chris. And it does depend quite a bit on where storms ultimately formed. Last year, I would say, was a relatively normal year for the number of storms that formed out between South America and Africa. And it's usually those storms that have impacts, if there are going to be any, to Puerto Rico and the Virgin Islands. But we've had so many disturbances that did not form into storms before they reached to Puerto Rico and the Virgin Islands, and instead waited until the Western Caribbean or the Gulf of Mexico before they did so. So the impacts to any one given location do tend to be very dependent upon where the storms ultimately formed within the basin.
Okay, I think we have one final question coming in. You mentioned your UWM class. What career roles have your students gone into within the meteorology field, and more specifically with hurricanes?
Yeah, that's a great question as well, Alex. A lot of our students at UWM have gone into careers with the National Weather Service, whether they're in the Southern United States office that deals more frequently with hurricanes and tropical storms, or more commonly here in the Midwest, where we are dealing with more things like cold and snow like we have seen lately. A very large percentage, 40 or 50% of our graduates have gone into the National Weather Service. So whether you're in the Milwaukee area, Green Bay area, elsewhere across the Midwest, it's a high likelihood if you're seeing a product come from the National Weather Service, there's at least one person from UWM somewhere behind that. We also have a lot of students who go into more research-oriented careers. Some become faculty at universities. We have faculty members at Northern Vermont University in Linden, the University of Nebraska, as well as the Naval Postgraduate School out in California. We also have some that become scientists at places like where I did my postdoc, the National Center for Atmospheric Research. And an increasing number are becoming employed in the private sector by consulting firms and scientific organizations that seek to provide sort of more applied science, in other words, to governments or to other companies that are weather and climate sensitive. Those students are finding jobs with those companies that help translate the science into actionable information. So we have quite a wide range of careers that students go into. Not as many have necessarily gone into hurricane-specific careers, but we have had the opportunity to work with hurricane scientists, both at the National Hurricane Center as well as at UW-Madison and their Cooperative Institute for Meteorological Satellite Studies as part of their graduate and undergraduate research.
That's fascinating. That was a great question, Alex, because I think people tend to think of traditional kind of meteorologists you might see on local news is the first thing that comes to mind, but there seems to be quite a wide breadth of opportunities for students who pursue a degree like this. Just actual final question, sorry, sneaking one in on you. Can you just speak a little bit about your work with the Northwestern Mutual Data Science Institute?
Yeah, I could speak a little bit about that. So the Northwestern Mutual Data Science Institute brings together practitioners related broadly to data science, both at UWM as well as Marquette. And my background in data science is primarily bringing together meteorological data like with hurricanes, or what we call data assimilation, which is taking observations like at what you see at airports or from weather balloons, and combining them with model information to be able to help run a computer forecast model to be able to forecast the future weather. And so my engagement is primarily through that expertise. The Northwestern Mutual Data Science Institute is bringing together scientists, not just in the atmospheric sciences like myself and a couple of my colleagues, but across a lot of other different disciplines to be able to organize student engagement as well as research opportunities. I personally have yet to have a research opportunity that matches specifically to my interests and expertise, but I'm always on the lookout. So it's a great initiative that Northwestern Mutual has supported, and I look forward to seeing where it goes in the years ahead.
That's great. It's nice to see such cross-disciplinary work pairing with local industry. We have a really strong volunteer group at Northwestern Mutual and over 2,000 alumni there. So just another example of a good partnership. Thank you for your expertise, which clearly is vast. It was kind of nice to think about something tropical today as we look out on our giant snow piles in Milwaukee. And we really appreciate it. We'd love to have you back another time. For everybody on the call, please join us again in March. We are featuring Chris Cornelius from the School of Architecture. His topic is fascinating. Its design is ceremony. I think that's one that you don't want to miss. So thank you again, Professor Evans. We really appreciate your time today.
Thank you very much, Amy, and thank you to everybody for tuning in. I appreciated the opportunity to speak to you all.
All right, take care. Thank you.
Bye-bye.